What if an AI model worked perfectly during training but failed in real life? That is exactly why testing an AI model is extremely important. Testing is the process of checking how well a model performs. It happens after training is completed successfully. Without testing, there is no way to measure true intelligence. A model may look accurate during training, but fail on new data. Testing reveals whether the model actually learned patterns correctly. The main goal is to evaluate real-world performance. AI models must handle unseen data effectively. If they cannot handle new data, they are not useful. Testing uses data that the model has never seen before. This data is called test data in machine learning. Test data is kept separate from training data completely. This separation ensures fair evaluation of performance. The model makes predictions on this hidden data set. These predictions are then compared with correct answers. The difference between them shows how accurate the model is. This accuracy helps determine if the model is reliable. Testing helps detect overfitting problems in AI systems. Overfitting happens when a model memorizes instead of learning. A memorized model performs poorly on new examples. Testing exposes this weakness clearly. Good testing ensures the model can generalize properly. Generalization means performing well on unseen situations. This is the ultimate goal of machine learning. Testing is not just a final step, but a critical process. It validates whether training was successful or not. Without testing, developers cannot trust model results. Real-world applications depend heavily on proper testing. Self-driving cars must be tested for safety and accuracy. Medical AI must be tested for correct diagnosis performance. Financial models must be tested for prediction reliability. Even small errors can lead to serious consequences. That is why testing standards are extremely strict. Different types of testing are used in AI development. Each type focuses on a specific aspect of performance. Some tests measure accuracy under normal conditions. Others test performance under difficult or unusual situations. Stress testing checks how models behave under extreme input. Robustness testing checks stability against noisy data. These tests ensure the model is strong and reliable. Performance metrics are used to evaluate results. Accuracy, precision, and recall are commonly used metrics. These metrics give a clear picture of model quality. High accuracy alone does not always mean a good model. Balance between different metrics is important. Testing also helps compare different AI models. Developers choose the best performing model based on results. This selection process improves overall system quality. Testing also identifies weak areas in model performance. These weak points guide further improvements. Developers may retrain the model to fix issues. Testing and training often work in cycles. Each cycle improves model accuracy and stability. Real-world data is often more complex than training data. Testing prepares the model for these real conditions. It ensures the model behaves consistently in practice. Continuous testing is important even after deployment. AI systems must be monitored over time. Data patterns can change in real environments. This is known as data drift in machine learning. Testing helps detect such changes early. Early detection prevents system failure. Reliable AI systems depend on strong testing frameworks. Testing transforms trained models into usable tools. It bridges the gap between theory and reality. Every successful AI system goes through strict testing. Testing ensures safety, accuracy, and reliability. It is the final quality check before real use. Strong testing builds confidence in AI technology. Developers rely on testing results for decision-making. Users depend on tested systems for real applications. Testing is what makes AI practical and trustworthy. Now you understand the basics of testing an AI model. Now we explore how datasets are split for proper AI testing. One of the most important ideas is the train-test split. The dataset is divided into training and testing parts. The model learns from the training data first. Then it is evaluated using unseen test data. This separation ensures fair performance measurement. If the same data is used for both training and testing, results become biased. That would make the model look better than it really is. Test data acts like a real-world exam for the AI. It checks whether the model truly learned patterns. A key goal of testing is detecting overfitting. Overfitting happens when the model memorizes training data. A memorized model performs poorly on new data. This is one of the biggest problems in machine learning. Testing reveals this issue clearly and accurately. Another problem is underfitting. Underfitting happens when the model learns too little. It fails to capture important patterns in data. Such a model performs poorly even on training data. Good testing helps identify both overfitting and underfitting. A balanced model performs well on both training and test data. That balance is called generalization ability. Generalization is the main goal of AI testing. Models must work well on unseen, real-world inputs. Testing simulates real-life conditions for the model. It shows how the model behaves outside training environment. Randomized test data improves evaluation fairness. It prevents memorization of specific data patterns. Cross-validation is another advanced testing method. It divides data into multiple folds for repeated testing. Each fold is used as both training and testing set. This gives more reliable performance results. Testing also helps identify data leakage issues. Data leakage happens when test information leaks into training. This creates unrealistic performance results. Proper testing prevents this serious evaluation mistake. Another key idea is model robustness. Robust models perform well even with noisy data. Real-world data is often messy and incomplete. Testing includes adding noise to simulate real conditions. Stress testing checks model behavior under extreme cases. This ensures the model does not fail unexpectedly. Performance consistency is also measured during testing. A good model gives stable results across different datasets. Instability indicates weak learning or poor data quality. Testing helps improve reliability before deployment. It acts as a safety check for AI systems. Developers use test results to refine the model. Poor performance leads to retraining or adjustment. Testing and training often happen in repeated cycles. Each cycle improves model accuracy and stability. Test results are compared using performance metrics. These metrics turn predictions into measurable values. They help evaluate model strength objectively. Testing ensures decisions are based on evidence, not assumptions or guesswork. In real applications, testing becomes even more critical because errors can have serious consequences. Self-driving systems require extremely strict testing. Medical AI must pass high accuracy standards. Financial systems must be tested for reliability. Even small errors can lead to major losses. That is why testing is never skipped in AI development. It ensures models are ready for real-world use. Testing builds trust between AI systems and humans. It verifies that learning was successful. Without testing, AI models cannot be safely deployed. It separates useful models from unreliable ones. Proper testing improves overall system quality. It reduces risk in real applications. Testing is a core part of machine learning development. It transforms theory into practical reliability. Every strong AI system depends on rigorous testing. Testing ensures real-world readiness and safety. Now you understand train test split and overfitting in AI testing. Now we explore how AI models are carefully evaluated during testing. Testing is not just one step, but a detailed evaluation process. One key part of testing is called validation. Validation checks model performance during development before final testing. It helps fine-tune the model for better accuracy. Validation data is separate from both training and test data. This ensures the model is evaluated fairly at every stage. Developers use validation results to improve model settings. These settings are called hyperparameters in machine learning. Hyperparameters control how the model learns from data. Adjusting them can significantly improve performance. Testing also relies heavily on performance metrics. Metrics are numerical values that measure model quality. They help convert predictions into measurable results. One common metric is accuracy. Accuracy measures how many predictions are correct overall. However, accuracy alone is not always enough. Some problems require more detailed evaluation methods. Precision is another important metric in testing. Precision measures how many predicted positives are actually correct. High precision means fewer false alarms. Recall is another key metric used in evaluation. Recall measures how many actual positives were correctly detected. High recall means fewer missed cases. Precision and recall often work together in analysis. A balance between both is important in real systems. Another metric is F1 score. F1 score combines precision and recall into one value. It helps evaluate overall model balance. Different applications require different evaluation priorities. Medical systems may prioritize recall over precision. Spam detection may prioritize precision over recall. Choosing the right metric is critical in testing. Confusion matrix is another important evaluation tool. It shows correct and incorrect predictions in a table format. This helps visualize model performance clearly. Testing also includes error analysis. Error analysis identifies where the model makes mistakes. Understanding errors helps improve future training. Some errors may come from poor data quality. Others may come from model limitations. Validation helps detect these problems early. Cross-validation is another advanced testing technique. It splits data into multiple parts for better evaluation. This ensures more reliable performance measurement. It reduces bias from a single data split. Testing also checks model stability. Stability means consistent performance across different datasets. A stable model performs well in many situations. Unstable models may perform well only in limited cases. Robustness testing checks performance under noisy conditions. Noisy data simulates real-world imperfect input. This ensures the model is practical in real environments. Another important aspect is generalization testing. Generalization checks how well the model handles unseen data. This is the ultimate goal of machine learning evaluation. Overfitting becomes visible during poor test performance. Proper testing helps identify both problems clearly. Developers then adjust the model accordingly. Model comparison is also part of evaluation. Different models are tested to find the best one. The best model is selected based on metric performance. Testing ensures decisions are based on evidence, not guesswork. Real-world readiness depends on strong evaluation results. Even small metric improvements can be very important. Testing helps optimize models for specific applications. It ensures reliability before deployment in real systems. Without proper evaluation, AI systems may fail in practice. Testing builds trust in AI predictions and decisions. It transforms raw models into reliable tools. Developers depend on testing to guide improvements. Users benefit from accurate and stable systems. Evaluation is what confirms true model intelligence. Now you understand validation metrics and performance evaluation in AI testing. Now we explore what happens after an AI model passes testing. Passing tests does not mean the model is finished forever. The next step is deployment into real-world environments. Deployment means the model starts working with live data. Real-world data is often different from training data. This difference can affect model performance unexpectedly. That is why post-testing monitoring is extremely important. Once deployed, the model must be constantly observed. This process is called continuous monitoring. Monitoring checks if the model is still performing well. Even a successful model can degrade over time. This problem is known as model drift. Model drift happens when data patterns change over time. For example, user behavior may evolve in digital systems, or financial trends may shift in unpredictable ways. Continuous testing helps detect this early. Early detection prevents serious system failures. Another important concept is data drift. Data drift occurs when input data distribution changes. This directly affects prediction quality. Monitoring tools track these changes automatically. Alerts are triggered when performance drops. Developers then investigate the cause of the issue. Sometimes the model needs retraining with new data. Retraining helps the model adapt to new patterns. This keeps the system accurate over time. In many systems, retraining happens regularly. Some models are updated weekly or even daily. Continuous improvement is part of AI lifecycle. Another key idea is A/B testing in AI systems. A/B testing compares two different model versions. One version is old and one is newly updated. Both models are tested on real users. Their performance is compared carefully. The better performing model is selected. This ensures only improvements are deployed. Real-world testing is more complex than lab testing because real environments are unpredictable. Users interact with systems in unexpected ways. This creates new types of input data. AI models must handle these variations effectively. System reliability becomes extremely important. Even small errors can affect large user bases. That is why safety testing is critical. Fail-safe mechanisms are often added to AI systems. These mechanisms prevent catastrophic failures. Logging systems record every model prediction. Logs help analyze errors after deployment. Engineers use logs to improve future versions. Performance metrics are still tracked after deployment. Accuracy, precision, and recall continue to be measured. Real-time dashboards display model health. This helps teams react quickly to issues. Testing never truly ends in AI systems. It becomes a continuous lifecycle process. Feedback loops improve system accuracy over time. User feedback is also collected for improvement. This feedback helps identify hidden problems. Real-world usage reveals weaknesses not seen in labs. Developers fix issues through updates and patches. Each update requires fresh testing before release. This ensures stability in production environments. Without monitoring, models can silently fail. Silent failure is one of the biggest risks in AI. It means the system looks fine, but performs poorly. Continuous testing prevents such hidden issues. Strong monitoring ensures long-term reliability. AI systems must evolve with changing data. Static models quickly become outdated. Adaptability is key for modern AI success. Testing and monitoring work together continuously. They form a safety net for AI systems. This keeps models accurate, safe, and useful. Now you understand deployment monitoring and real-world AI testing lifecycle. Now we explore what happens when AI models fail during testing. Failure is a normal and important part of AI development. Testing is designed to discover weaknesses in the model. When a model performs poorly, developers begin debugging. Debugging means finding and fixing problems in the system. The first step is analyzing incorrect predictions carefully. These errors show where the model is struggling. Some errors come from poor quality training data. Other errors come from incorrect model design. Sometimes features are not properly selected for learning. Feature selection affects how well the model understands data. If important features are missing, accuracy drops significantly. Developers often retrain models with improved datasets. Better data usually leads to better performance. Another common fix is adjusting model parameters. These adjustments are called hyperparameter tuning. Hyperparameter tuning improves learning efficiency. Even small changes can greatly improve accuracy. Testing also reveals bias in AI models. Bias means the model favors certain outcomes unfairly. Bias often comes from unbalanced training data. Detecting bias is an important part of testing. Developers work to reduce unfair behavior in models. Another issue is variance in predictions. High variance means model predictions are inconsistent. Testing helps identify unstable behavior early. Engineers then apply regularization techniques. Regularization reduces overfitting and improves stability. Dropout is one common technique used in neural networks. It randomly disables neurons during training. This forces the model to learn more robust patterns. Another method is early stopping. Early stopping halts training when performance stops improving. This prevents the model from overlearning noise. Testing also compares different model architectures. Some architectures perform better for specific tasks. Choosing the right model is critical for success. Experimentation is a key part of AI development. Developers run multiple tests to compare results. Each test provides insights into model behavior. Performance improvements are often gradual. Small improvements can have big real-world impact. Testing also includes stress testing scenarios. Stress tests push models into extreme conditions. This helps check system reliability and safety. Robust models perform well even under unusual inputs. Weak models fail quickly under stress conditions. Error analysis is another important testing tool. It categorizes different types of mistakes. This helps developers understand failure patterns. Once patterns are known, fixes become easier. Testing results guide future model improvements. Continuous iteration is essential in machine learning. Models are rarely perfect in the first version. Improvement comes through repeated testing cycles. Each cycle increases accuracy and reliability. Real-world feedback also helps improve models. User interactions reveal unexpected errors. These insights are valuable for refinement. Testing is closely tied to model optimization. Better testing leads to better optimization decisions. Strong models require both training and evaluation. Without testing, improvement is impossible. Failure is treated as learning information in AI. Every mistake improves future model performance. Developers rely on testing to guide decisions. Testing reduces uncertainty in AI systems. It ensures models are safe and effective. Reliable systems are built through repeated correction. AI becomes stronger through continuous improvement cycles. Debugging transforms weak models into strong ones. Testing reveals truth about model capability. It separates good models from unusable ones. Improvement depends entirely on accurate testing. Now you understand debugging failures and improving AI model accuracy.